Oh, here's what it looks like when I'm loading your YouTube video. Then I got to wait for it to process and then all that kind of stuff. But we can still go on with the with this. All right. So um, what I'm processing, this was part one. Now what we're doing now is part two. So this would be track 12. All this stuff. Science and math of Bolt. My boy. Part two. If it finds out that he was using steroids, I'll I'll be heartbroken. I mean, just heartbroken. All right, but anyway, because he's my boy. All right, so let's take a look at this. So we can look at some accelerations and things like that that are just crazy. Now, this is from Wired Magazine. Well, now what we're going to do is we're going to look at some crazy stuff here. All right, and the we're not going to worry about a lot of because this is actually physics that's written about the 300 level course. I mean, this would be a great little thing for my for our students taking physics 310 mechanics type thing. Now here's the friction force. This is what the runner is pushing back, and then he's getting pushed forward by the so the fake force is what he's pushing back with, and going forward is what's causing him to go forward with the frictional force. And then we've got mg going down. So we had to add that fake force just to make it all work out. And anyway, so the frictional force mu of s times mg, and we get the angle. And if these angles come out to be 45 degrees, their initial acceleration is amazing. It's almost 1g. These guys almost take off at 1g. It doesn't last long. It lasts for probably a tenth of a second or 0.9 seconds or something like that. But they do it for that amount of time. Oh, I didn't finish that car problem, did I? I just showed you how to do the acceleration on the car. We're going to look at some other things on the car here in a minute. All right, so, and if the runner goes at distance s, so you got the average time times the seconds, all that kind of stuff. But that was what I wanted to show you, was that when they take off at this 45-degree angle, they're almost pulling off with 1g. But now let's look. So here's his actual position versus time graph. And when it curves like that, that shows right here is where a lot of the acceleration took place. It's almost at a constant speed for the last few seconds, and then he actually drops off. Because when you look at this, this is their actual speed versus time graph. So this gives us a graph of their acceleration, what the acceleration actually looks like. So when he's at about 5.5 meters per second at 1 second, so it took him 1 second to get up to 5.5 meters per second. But there's actually it's almost infinitesimal. Boom, out of the blocks. Now this is a huge acceleration. Look at this. In less than so what is that speed limit? That's about 9.8 meters per second. This was about 5.5 meters per second, and it looks like this time interval might be what, 0.7 seconds or so. You divide this change divided by the change in time, so you get that little triangle here. Rise or the run, remember that? Yeah. The acceleration on the speed versus time gives you your slope of the line, and so that gives you your acceleration. Now notice acceleration is not constant. In fact, he's accelerating less and less and less, and then he's going at a constant speed. Here, it looks like there's about almost 2.5 seconds where he's at a complete constant speed, and then look what happens. They start to slow down. Right here is where the race is won, too, because what are we talking? We're talking about at 8.6 seconds to 9.7 seconds or something like that. Right here is where even at the high school level, even with our elite high school runners, this is where the race is won. Whose line dips the least? In other words, who can maintain less deacceleration? Who can slow down the slowest wins the race? It's an interesting thing. All right, I just wanted to share that because we're going to look at that in our last problems. Right now you're going, what the hell? We're going to have to calculate this? I'll walk you through it. You'll be fine. And it'll be fun. It'll be so cool. I'm pushing boundaries here. All right. Yeah, you're my guinea pigs here. I just found this to be a fascinating thing. All right, so let's go back to the Barabbas car here. All right. Let's take a look at that slide real quick. 1,236. All right, so now here's what I want to do. Here's what I want to do. With this Barabbas car, we've already got the acceleration of between that 0 and 60 of 16.1. All right, so do you have all this again? 16.1 meters per second. All right, there it is. This is on page 3. Now let's go to page 4 of the notes here. All right, so 4 says this. All right, the mass was 1,230 kilograms. The acceleration was equal to 16.1 meters per second squared. All right, the final speed was 26.8 meters per second. We should be able to calculate the horsepower of this car if we can take the force times the velocity. And now what we came up with was what the power of the car was. The force times the velocity. And I'm assuming a constant acceleration for that amount of time. All right. So the force would equal m times a. And then the speed is 26.8 meters per second. And this is going to be mind-blowing. When we do it for the Bugatti, you'll find that we actually hit it pretty good. But this one, I don't know, because I got 1230. The Bugatti only had like an acceleration of about a fourth of this, times 16.1 times 26.8. No, that's just crazy. It does not have a horsepower of 530,000 horsepower. I'm sorry. Even though that's the acceleration we calculated, that acceleration does not go for that long. That acceleration does not go for that long. So this is bogus. But what we come up with, the Bugatti, is probably correct. All right, so what I want you to do is enjoy the Top Gun video. I mean, it's hilarious. They're racing a Bugatti against a Euro fighter jet, and it's just amazing. And then the last video we'll be walking through your homework assignment. Okay, don't be afraid. It'll be fine. This is really cool. All right, so out here on this.